Otherwise, these elliptical galaxies, for example, they exhibit a uniform distribution of luminosity, uniform distribution of light and nothing more. And basically, they are the earliest type, mostly composed of hydrogen and very lighter elements, and very less percentage of higher elements formed during the very evolutionary phases, first phases of the formation of the universe. Now, the dynamical evolution, the word dynamical itself implies what happens to the state, to the current state of a galaxy, say after one orbital period. Orbital period simply meaning, for example, galaxies can exist as isolated systems or they can exist in groups. They rotate about themselves and they go around a common center of mass in a cluster of galaxies. So in such a case, what happens to the structure and morphology, that is the shape of galaxy, after one complete period? And this is nothing but the dynamical evolution. Now here we see disk galaxies which look entirely different from the ones we have seen. For example, here we are able to identify some components like a spiral structure, or here for example bar-like features and some appendages, and here for example we can see the disk very clearly. So these are not like elliptical galaxies. They have got higher element in very high percentages, means they evolved at later stages in the universe, we can say. And these appendages and all these things, for example, these are the structural deformations. Structural deformations in the sense, after, say, during their lifetime, one orbital period or two orbital periods, they interact with neighboring galaxies. And during such interactions, the galaxies may get damaged either temporarily or permanently, leaving such relics behind. Here, in this snapshot, for example, we look at some galaxies which are interacting, which are close by, and they interact with one another, leading to either destruction of one galaxy or leaving one galaxy short of mass. For example, here we can see, termed as the mice galaxies, we can see appendages. Actually, what we are looking at is one particular evolutionary state, and this is just transient. Of course, the process continues for millions of years, just one transient state. Now here, at the center, we will see two galaxies in close proximity, and they are referred to as dumbbell systems. They look like dumbbell. And we don't expect these galaxies, which are huge, to be stable in close proximity. But weird things happen in the universe in such cases. That is, the dumbbell systems are intrinsically stable. So what factors contribute to such intrinsic stability? And this also comes under the dynamical evolution of such galaxies. Now here, just to give you an idea, I would like to summarize a particular method. For example, we use a particular methodology called collisionless dynamics. Meaning, here collision means we are not referring to one galaxy either interacting or colliding with one system. We just take an isolated galaxy, and there are billions of stars in a galaxy which are in constant state of motion, and they exercise gravitational influence on one another. When we study the evolution on a dynamic time scale, which is about 10 power 8 in the case of a normal galaxy, we can certainly expect the gravitational influence of some stars on other stars. But in order to simplify things, in order to get some results, we will assume that there are no gravity interactions between stars. So such systems are referred to as collisionless systems simply. So in this approach, you can see we study the motions of large number of point particles. For example, in the morning, Professor Hassan spoke on simulations of galaxies, where each star is represented as a point mass. So stars are represented as point masses, either for numerical calculations or for simulation purposes. So, and they orbit around one center under the influence of their mutual self-gravity. That means no external agency like a nearby galaxy or group of galaxies is influencing. Only their self-gravity is sustaining the system. This is a simple assumption, that is collisionless dynamics. And using this, these are the examples. For example, I have already shown you the images. Ellipticals, disk galaxies, even globular clusters, which are composed of enormous number of stars and clusters of galaxies. And what are the goals? With this assumption, we are going to inform mass distribution from observed kinematics, meaning we study the motion of the representative particles, say for one orbital period, for one complete rotation, and of course we also keep in mind an external agency like another galaxy, and we study the gravitational interaction between the two, because if the universe contains only one galaxy, then there is no force altering its state of evolution. We are expected to include an external agency which influences. So we study the kinematics of the stars, and we will try to arrive at a conclusion about the mass distribution. That means what is the mass initially and what is the mass say after some time, and we will try to find out what is the mass loss and what happened to this mass, all these things, and we will try to understand the changes in the structure of galaxies. So with this way we learn about galaxy formation, how they came there in the first place, and second, the stability of galaxies. So what is going to happen then if one galaxy happens to be in a dumbbell system, or in a small cluster, or in a large cluster. Now here what we are going to do, first thing, the two circles represent two galaxies, and here S represents a representative star. For simplifying things, there are several such stars. Only thing is, you pick a sample of stars, pre-decided. These many number of stars that I am going to use in order to make my model of evolution, and then we are going to study the effects of this galaxy on this particular star. That means an external galaxy is exercising gravitational force, you can see. Now we are going to study its kinematics, its motion, and we are going to study its orbit and any changes in its orbit during one orbital period. Which means, is the star going to escape this galaxy because of this, let us say, proximity, close proximity, or is it going to move towards the center or away from the center? All these things can be brought out by simple numerical calculations, of course, which will be complemented by simulations. Here now we can see first a snapshot of the initial condition. Simply, this is what is called a statistical description of the system, because according to the collisionless model, we can see here what we are going to do is, you have seen the two circles. We divide the circles as concentric circles into several layers, just like an onion. And then we are going to study, we are going to use simple Newton's laws of motion, simple, nothing more. And of course we need to calculate the acceleration the force, the gravitational potential and everything, and for which actually we already defined a gravitational potential, which also has got a particular model. There are several models and we need to select one model, one gravitational potential, one variety which fits our model, and depending on that what you do. For example, here there are some representative stars you can see. Each galaxy is subdivided into concentric shells you can say, and we distribute the stars initially. Like they are stationary, they are not moving at all. Now we are going to set them in motion and observe the changes. So you can see these are all shells. The numbers refer to different radii from the center. That is from the center to 0.05 different cells we are getting. Next. Now here, this is the snapshot after one orbital period from my current point. We can definitely say, next, previous. Here you can see, for example, 24, 24, 24, 24. Equal number of stars. We distributed them across the galaxy at different distances. Now here you can see how the distribution changes. That means the stars which are very near to the center, they remain there. Meaning the gravitational influence of the other galaxy is minimal on those stars which are very near to the galaxy than on those stars which are in the shells away from the center. As you can see, the distributional changes. Now this directly relates to the mass distribution. That means here we are studying how the mass is changing, say during one period, one orbital period. Next. Now next thing what we are going to do, we need to study the orbits of stars, for which actually with the given gravitational potential we are going to develop what are called surfaces of section or zero velocity surfaces. Meaning we have seen 24, 24, 24, 24 stars, let us say in 4 shells. Now as per the laws of motion, the stars, let us say in the second shell, unless there is a disturbing force, they tend to remain in that shell and they don't move out. That means they are limited to a particular region of space in galaxy, or you can say they are limited to a particular section. So the surfaces of section will give us what are called these surfaces. This is one surface, this is second one, this is third, fourth, and this is another one. All these surfaces, they have areas between them. You can see no two surfaces of section or zero velocity surfaces, as they are called, they intersect. There are regions inside these sections within which only the stars can move, and they cannot escape until unless there is a large tidal force from the other galaxy. So here we see some numbers. These numbers represent the energies of the zero velocity surfaces. Now why they are called zero velocity surfaces? Simple thing. If you keep a star, say on one of the segments, on one of the lines, it stays there permanently. So that's why they are called zero velocity surfaces. Next. Now with the statistical description that we obtained, we have to calculate the changes, the mass distribution and the energy changes. For example, you can say initial the energy changes are given. The kinetic energy, the potential energy, the binding energy and the total energy. This is initial and this is final. We can see clear differences. And from this we conclude, say after one orbital period in a dumbbell system or in group of galaxies, this is what is going to happen to the member galaxies. member galaxies, that too mostly less massive members of a cluster of galaxies. Next. Now here, the mass distribution function is given. Solid line representing the initial distribution and the dashed curve representing the changes. Next. And here, for example, simple graphical representation of the positions of different stars. Simple on planar axis, we represent the stars. You can see these numbers 1, 2, 3, 4, 5. They are nothing but the distances from the center of the galaxy, or they represent different shells into which we subdivided each galaxy. Next. And the one we saw was the initial snapshot. Now this one you can say at t is equal to p. P is nothing but one period. We can see the distribution. So that means completely the galaxy completely got disturbed. Next. Now here, the same zero velocity surfaces can also be used in order to plot and study the trajectories of representative stars. For example, here in this snapshot, the star number is given here. That is the 65th one. These are its various coordinates. Like for example, the phase space coordinates. The first three will give you the x position, y position and z position in galaxy, and the last three numbers will give you the velocity components. That means its velocity along x-axis, y-axis and z-axis. And we use an algorithm and plot, for example, each dot, each star that you see here. These are the two galaxies, let us say. Each star, each star-like thing there are not many. It is just one star, but different positions at different points of time during this one orbital period. So as we can say, for example, this 65th star is very much bound to the center of the galaxy, or very near to the center of the galaxy, and we cannot expect any dynamical changes in it. Next. Now here, if you take the 78th star, we can see its migration. Now what we have to do actually is we need to imagine these surfaces as three-dimensional. Then we would be able to feel, we would be able to estimate this particular motion. For example, one star, you can see it's like leaving the entire system. Three-dimensional, because the star happened to gain some energy because of the gravitational interaction. So the gravitational force changes the way the galaxy rotates, either increasing or decreasing its kinetic energy or potential energy, which automatically gets transformed to its residents, that are the stars. So this is a simple basic methodology to study the dynamical evolution of galaxies. Any questions? Yes.
So you said that the elliptical galaxies have only hydrogen, helium and very less lighter elements.
Yes.
It means that the planets in those galaxies can't have any life.
The
Planets in the elliptical galaxies. They can't
planets in the elliptical galaxies. Now, I don't actually, I am unable to recollect any planets that we found in elliptical galaxies. Are there any?
It should be there.
In the elliptical galaxies, but they
No,
would be just like
there is
the-
nothing about elliptical.
No.
No, see, they should be there. We don't know because we are still observing planetary system within our galaxy.
Yes.
Forget the elliptical galaxy.
Yes.
We don't
But
have
there is no
knowledge.
reason why they
But
should
there-
not be.
Yeah,
Yes.
but there is no reason why they should not be.
Yes.
No, what he is saying is if there are no heavier elements, then planetary formation can't take place. But not all elliptical galaxies are only of height.
Mostly light elements. So if we have planets, we can expect them of the nature of Saturn, Jupiter.
No, it's not true. See, many ellipticals can be merger elements.
Yes.
They have everything there.
No,
Yes.
and basically they are there. They are about stars.
Yes.
Yeah, so
There is
that-
heavier elements. That are
Yes.
they have,
And one thing is basically they are devoid of any gas.
No, that is
Not necessary.
that is also changing now. Earlier they said that elliptical galaxies
Yeah.
are devoid of gas, but
Yes.
now they are finding gas.
Yes. Any other questions?
Sir, how you say the particular star is in center in the universe?
In the center,
In the center of the universe.
Center of
How you say the particular star is in the center of the universe?
universe or galaxies, we are referring.
No, universe.
Universe.
Not galaxies.
See, one thing that I don't know how to represent the center of the universe.
Okay.
You should ask cosmologists.
Okay.
Would you like to throw some light on this?
There is nothing called the central.
Okay, center of galaxy.
See, center of galaxy, yes, you can take.
That
Because it's a clear-cut mass distribution. At least you know the visible dimensions of the galaxy, so you can fix.
And where is the place of the Earth in the universe, or in the center of the galaxy?
Earth belongs to Milky Way,
Okay.
which happen to be a disk galaxy, and it's about 8,000 kiloparsecs from the center of the galaxy, which is the current position of the Sun. And as you know, Milky Way is nothing but an average-sized galaxy.
Yeah.
In the local group of galaxy,
Yeah.
which has about 40 members. So small group, small cluster, and this is part of a large cluster. So there are thousands and even millions of such large clusters. Okay.
Actually, what's there in the center of the galaxy?
And
What's actually there in the center of the galaxy?
yes, the center of the galaxy is the place for a lot of activity. A lot of activity, that is what we call, for example, right now they say that there could be a supermassive black hole at the center of each galaxy. That means a highly evolved state of matter, you can say.
Yes, sir, but
And-
black hole, but Stephen Hawking's latest theory says that black holes don't exist.
Of course, see, the thing is, black holes don't exist or don't form. Sir is the right person to comment on that.
Look, it need not be a black hole, it can be a very highly compressed, whatever it is.
Because the density of matter near to a galaxy is very high, and it can exercise its influence on other parts of the galaxy. Okay?
So your model of the collisionless systems was always equivalent to field-field interactions other than particle-particle interactions. That's it.
Not field, it's actually particle.
But there is no
Gravitational interaction.
That's it.
One mass
Field-
interacts with another mass.
A field interaction only.
No, we cannot say that.
Because you're telling it's collisionless, it's field interaction only. There is
No.
need for us to
Collisionless in
again
the sense,
nomenclate.
collisionless in the sense, we make an assumption initially, just to study the basic dynamics, that there are going to be no collisions. Next aspect is you need to introduce collisions, then study, because there is no ideal collisionless system in the universe. There is no ideal. This is ideal case. So first you develop based on ideal model and then include various other parameters. Yes.
The spherical or elliptical shape of the galaxies is by nature or by any gravity?
By nature. By nature in the sense, for example, by their morphology. How they appear to you.
You see, gravitation is isotropic. So it will be more or less the same in all directions. It won't be that it's much less in one direction and much more.
Yes.
Once after the star reaching a zero velocity zone, how long it will sustain in this state, and what is going to disturb that state after reaching that zero
Yes.
velocity?
Again, it depends on the surroundings.
And other galaxies
See,
influence are
using only ideal conditions, let us say, for example, the collisionless model. I found that after 2 orbital periods, even those stars well within zero velocity surfaces which are not disturbed earlier, I found them a displacement in their position.
then when you are saying that in zero velocity state,
Yes.
how long it is going to sustain in that
One thing, everything is decided by its energy. And once the star gains energy, there is nothing that can stop it.
The word is oversimple.
And over time, during few orbital periods, the stars are bound to gain energy. For example, you have seen
That means zero state is going to be a momentary.
Yes,
It is not a permanent.
it's a state of representation.
Yes.
That means first of all you are deciding these are the areas. These are the areas that the stars are expected to be stationary or expected to be bound within. And later you study by introducing various disturbing elements, disturbing factors.
This other galaxies also, the
Yes.
attractive forces also may disturb it from there.
Yes.
As per Friedman's redshift that the particles are moving away, would there really be a big crunch?
No, I am not the right person again. You can ask. You should ask a cosmologist.
We have to go by observation. And right now, the observation says that there will not be a big crunch. That was the older.
Okay, we can then.
So, thank you very much for coming and participating in the lively discussion also. And we hope that next time we have such an event, we will keep you on our mailing list. Thank you very much.
Thank you, sir.